Thank you, Terry. So that the other people who have not been able to make it can actually watch it later. And as I also mentioned in B courses, my experience has been that the Unitary processes both the high-def version and simple definition version, standard definition version. And it takes quite a while for them to process high-def version. But you probably want to have high-def version to be able to read what I'm writing in the blackboard. Is that your experience too, if you have one thing? Yeah. So that may actually not appear for several hours, maybe even a day. So I hope you have some patience on that too. Okay, so let us get started, and we'd like to basically wrap up the whole discussions we have been doing on non-relativistic 2FT, hopefully today, and move on to the quantization of photon next week. And as you might notice, compared to syllabus, we're a little behind, but I'm sure we can make it till the end of the course. Okay, so what we've been doing last time was the look at the condensation of fermions. And if you have the gas of fermions, you cannot have a condensate like what we had for the boson. Which can have a condensate of zero momentum mode by itself. But in the case of fermion, we're always talking about the condensate, which is pairwise between momentum P and minus momentum P. And this is what is based on what is called the BCS theory. And there was a little confusion on the math I had when this was like it. So the idea is that you have this usual Hamiltonian. And let us not even look at the sum of momentum modes to simplify discussion today. And just focus on one momentum mode and its negative mode, P and minus P. Then I have a piece which looks like this. Then we are talking about a situation where there might be pairwise condensate, so that this thing, we have an expectation value, so that I will place this by a number, and I also consider this condensate, so I will place this by a number. So this whole thing would then lead to a term that looks like this. So that's what we talked about on Wednesday. So this original potential that shows the interaction among particles times the size of a condensate is described as delta. And by combining this usual piece of the free particle with the chemical potential, and chemical potential is positive, because we are talking about stacking up all the particles up to the chemical potential, that's the Fermi energy. And this parameter delta is called the gap. And the reason why this is called a gap, I mentioned briefly on Wednesday, but I will actually elaborate this on it a little bit more in a few minutes. So that's the Hamiltonian we're talking about. So we are using the same idea as we have used in the case of the boson. You are replacing some of the creation-relation operators by their expectation values in the presence of a condensate. And we keep terms in the Hamiltonian that are only up to quadratic orders in creation-relation operators. And high order terms, in certain circumstances, you can justify that they are negligible. And when that is the case, then this purely quadratic Hamiltonian, even though it looks kind of odd, and I'm mixing up C and D, I apologize. And what did I say? Well, that's right. As long as you can ignore high order terms in creation-relation operators, even though this Hamiltonian looks kind of weird because you have this B and B dagger pieces, but I have told you already that there is a transformation called Bogoliubov transformation that will allow you to completely diagonalize the Hamiltonian and work out the ground state and work on the excitation spectrum, pretty much everything you want to know about this. And I became aware that some of you have this feeling that this looks very, very complicated, but it's not. I hope you have seen that also in the previous problem of the Bogoliubov transformation for the boson. It is definitely complicated than dealing with the classical wave equation, but it's not that too much complication here either. So let's just look at it again. And I also screwed up one thing about the sign last time. So compared to the C of B over here, we introduce the C over here. Construction?
They're cutting wood.
Oh, okay. Whatever that is. I don't know what it's about. So anyway, so here I'm trying to emphasize that we are only doing a rotation. So in the case of the boson, we had Cauchy cinch. So that looked actually more like a Lorentz transformation. But here, this is just a rotation by an angle theta. That's why there's a minus sign over here. And this is a minus sign. I forgot the last time. It caused a little confusion. But I'm trying to make that clear right now. And using this, you can show that indeed these C operators as the usual canonical anti-commutation relations so the C and C dagger now qualifies as the creationalization operator for fermions. So then the only thing you need to do is to plug in form into this Hamiltonian. Then try to make sure that your Hamiltonian does not contain something like this. So your Hamiltonian now has some piece that looks like this. And here comes the excitation energy. And you make sure that there is no piece, this is 0, times CC. And constant. So once you make sure that this piece is not there, then your Hamiltonian looks like the usual form. That whenever create an excitation using creation operator, you waste energy. And you can annihilate the creation and excitation by this annihilation operator. So you can have the usual Hilbert space, where you have the ground state and you can create an excitation state, as long as this piece vanishes. So that's the main purpose of doing this Bogoliubov transformation. So you just plug in this rotated creation-annihilation operator in this expression, and collect the terms that look like CC, and make sure that all vanishes. So the idea here then is that I have this piece, which I for simplicity might just be not. Then inside this D dagger, I have CP. So then I have to solve this backwards. BP is CP cosine theta minus dagger minus sine theta. Dagger minus is CP sine theta plus C dagger minus cosine theta. This is is just the inverse rotation of this rotation up there, right? Then I plug these expressions into the Hamiltonian, and we collect the terms which we don't want. So these are the terms we want. We will want what inner is later on. But now we focus on this piece here and make sure that that combination vanishes. So out of this B dagger P, which is the Hermitian coefficient of this one, I have C minus B sine theta. So C minus B sine theta, CP cosine theta. And this is the point where you have to be paying attention to the order between operators because they anticommute. So if you have C minus B and CP here, here I have CP and C minus B. Instead, they come in the opposite order. So changing the order would actually cost me a sign. So this times this is this one dagger times that one, but by changing the order, I get minus cosine squared theta. Together with and from this one here, B dagger minus B has CP, and B minus B has CP cosine. So this actually gives me and also from that terms over here with the delta, BP has CP, B minus B has C minus B with a cosine for both of them. So that gives me minus delta, cosine and sine. Sorry. P. BP has CP cosine. B minus B is the dagger of this, so it has minus CP cosine. Is this right? I thought I was getting cosine sine. Let me put it anyway. PC. It's supposed to be cosine sine. So the first side is correct. The second line, BP. So this was supposed to be 2 cosine sine. Now I'm not getting it though. Why is that? Sorry, I got confused again. CP, that is correct. C dagger minus B. That is also correct. Going down. That also looks correct. Then go down here. Does anybody notice a mistake here? So this is supposed to become sine and cosine. Oh. Okay, thought I fixed it. Does anyone notice?
You
do, right?
Did you get extra minus sign for the sine 2 theta term?
This term?
Yeah. I mean, is that the problem? I'm not sure what.
No, here I wanted to get cosine sine times 2, but right now by plugging it here, I'm getting cosine squared. Is that wrong? So out of BP, I keep the term that looks like CP. And that seems to be cosine, right? And out of B minus B, that's a function factor for that bottom line. And pick up the BC minus B, that also seems to be cosine. So I get cosine squared. But I want to get cosine sine, which I did on a piece of paper, it came out this way, but somehow I'm not getting on the blackboard right now. This is embarrassing.
How do we get from the other left board?
Oh, I have the same question.
How do we get from there to
Here?
the left? Yeah. How do we get from the upper formula? Yeah.
So here, you assume that there is this pairwise compensate. So I replace this by a number. Then I find this term times a constant.
And we know it has to be real because delta has to be real?
Whether this has to be real?
No, because we're assuming the expectation value of B dagger P, B dagger minus P is the same as B minus P.
That's a good question. So in principle, this can be complex. And D is real because that was energy. So if I write this as delta as a coefficient over here, and the coefficient here in general is a complex quantity. So you're completely right. So that's a very good question, Jackie. So in principle, this is the complex. But once you see this Hamiltonian, there is also a symmetry of changing the phase of the creation-annihilation operator by the opposite phase. That does not change this Hamiltonian if you go back to its original form. And this is nothing but the number. So if I have e to the I theta n b, e to the minus I theta n, and I was going to come back and talk about the Lewis theory later on. Once you have a symmetry of changing the field to its phase, and once you have a symmetry, there is a conserved quantity. That's what Lewis theorem tells you. And you have to really look at this question. So that actually turns out to be the number operator, this n. So for a symmetry, you find a conserved quantity. But one step further, Lewis theorem tells you that once you have a conserved quantity, you can use this in exponent to generate that symmetry, namely this phase transformation. So once you have the conserved quantity n, you can put that in the exponent to define this unitary operator. In the same way that once you have a symmetry of translation in space, that's how you get momentum to be conserved. And if you put momentum on the exponent, then this is the unitary operator of shifting space. So the idea is always that once you have a symmetry in a Lagrangian Hamiltonian, you have a conserved quantity, and you use that conserved quantity to write down the transformation as a unitary transformation. And the way it works is that if we have a number operator, then you can use this Hausdorff's formula in multiple commutators. And this is B, and theta and B, and B is minus 1. So this is minus 1. this turns out to be getting minus I theta twice. And as a result, this sums up into the exponential. That's how you get this transformation. Because this was the symmetry of the Lagrangian to begin with. Hamiltonian also respects the symmetry, which is generated by this number operator. So if you change the phase of B, this Hamiltonian remains unchanged. But once you actually have the expectation value like this one, that corresponds to this expectation value delta. So what you're finding is that changing the phase of delta does not change physics, because that was a part of the symmetry. So you can always rotate the phase of the creation-annihilation operator in such a way that this is actually a real number without loss of generality. So that's why I have been already assuming that delta was real to begin with, but you can go through this argument why it doesn't change physics at all. Just by changing the phase of creation-annihilation operator, you can absorb the phase of this delta parameter, and you can take delta to be real without loss of generality. Does that answer the question? Who's question? Jackie, sorry.
Yeah.
Good. But I'm still having a problem with the cosine sign. I don't know what's going on here. Cosine squared, sine squared, that I got. Then I have B, Hermitian conjugate. Cosine side. That looks right. Yes, right.
So how you're getting the cosine is simply just replacing b of p by b of negative p, right?
Right.
But I think because it carries a spin index, so you should actually use the lower one with a dagger.
Right.
So that you'll get c. If you take the dagger on both sides, you'll get c of minus p cosine. Right?
Yes.
Then in that case, you're still getting cosine theta.
Yeah, so I'm still
Yeah.
getting cosine squared, right?
Yeah.
That's why I'm having a problem.
Mm.
Sorry about this. I have to fix it again on Monday, Wednesday. But anyway, this is supposed to come out to be cosine sine. So as a result, I did this yesterday on my notes too. I'm embarrassed that I can't reproduce it on the blackboard right now. So as a result, the coefficient of the first line sums up to cosine 2 theta. In second line is delta sine 2 theta. That has to vanish because you don't want to have this C term. And that tells you that tangent 2 theta is negative delta over E naught. Then cosine squared 2 theta can be written with the tangent 2 theta, the 1 plus delta squared over E naught squared 1. So that's where I can do the square root. Minus E naught as my convention, sine 2 theta is delta. So what that means, when when you come back to these expressions, then I'm going to erase this. Is that the spectrum we had for just filling up to the Fermi energy looked like this. This is E, and this is the Fermi momentum, and that actually came from folding over the particle to whole. That's what we discussed on Wednesday. So this is the situation we have. Now, when you actually hear E naught is negative because P is very small. This is negative and big compared to delta. Then this is more or less 1, which means theta is more or less 0. So as a function of P, cosine squared theta starts with 1. On the other hand, when E naught is now on the other end of large P, this becomes positive. This is negative sign. So this becomes minus 1. When cosine 2 theta is minus 1, theta is pi over 2. Then cosine squared theta goes to 0. So this happens around the Fermi momentum. And sine squared theta, of course, is the opposite of that. So that's where I made a mistake by factor of 2 on Wednesday. So when you are starting out with low momentum, cosine theta is 1, sine theta is 0. So then you have I made a mistake again. So this was supposed to be 1. Then you start over. So when I took the square root of this, I can choose the sign to be E naught, a positive here. And then using tan beta, tan 2 theta, this is actually negative instead, so I made a sign mistake, I apologize again. And when E naught is well before the Fermi momentum, this is largely negative, and therefore cosine 2 theta is minus 1. Then theta is pi over 2, which means sine squared theta is 1, cosine squared theta is 0. On the other hand, when E naught is large and positive, then this becomes 1, then theta is 0. That's when cosine squared theta is 1, sine squared theta is 0. So if you actually draw the lines this way, you find that your annihilation operator for small momentum is more or less just creation operator. And that makes sense because below the Fermi surface, you have to switch between particle and whole anyway. So your annihilation operator more or less becomes the creation operator. So that's the situation with very low momentum. If you go to very large momentum, then cosine theta is more or less 1. Then your annihilation operator of the excitation is more or less the same thing as the original annihilation operator. So that's the language of particles. And what we used to have in the particle hole is that this was actually the step function. So it used to be just hole over here and just particle up there. So there was a step function. But now in this BCS state, you have a continuous interpolation between the hole and particle. And the momentum is near this Fermi momentum. You have equal linear superposition of particle and hole. That's where you have this crossover. And so that's what's going on with the BCS state. So BCS state smoothly interpolates from the hole to a particle as you actually increase the momentum of the excitation, and all the actions are now happening near this Fermi momentum. Okay, any questions about this? I apologize, I went back and forth several times that I confused you, but I fixed the slides with more lines in between to make sure I got all the algebra so that you will see what's going on. Yes?
Why is there a minus on the 4BP side?
Here?
Yeah.
And that's because this is just a rotation. So cosine, sine, minus sine, cosine is a rotation matrix.
But if you take the dagger of C, it doesn't match.
Taking Hermitian conjugate doesn't change the sign.
I mean, like, if you take the first line, you can take the conjugate of the first line, right?
Taking conjugate of this one?
You can take the conjugate of C, CP, and see if it's the same with the second.
I'm not sure I can explain it very well.
Sigma-equality.
So you can take the conjugate of the first line and see if it corresponds to the second line. But there shouldn't be a minus sign if you just take the conjugate.
So we're assuming that theta is independent of p. But for p and minus p, theta is actually an odd function. But the main thing is that you have to make sure that this preserves the anti-commutation relation, and only with the minus sign that actually works out.
So whether it is C dagger P or not C dagger
No, C dagger P is still just Hermitian conjugate of one. So C minus P, that's the minus sign. But C dagger P doesn't have a minus sign. Okay? Thank you for the question too. And what that also means, that you know what the ground state is. So I erased this piece about the symmetries. Then the ground state is supposed to be annihilated by this new annihilation operator, which means that it is annihilated by this combination of dp cosine theta and d dagger sine theta. Then in terms of this is worked out, ground state is the state with no particles of p and minus p minus cosine theta minus the state with both states of built in with sine theta. So you can write this as a CP C minus P dagger 0, 0. So this is where you see this funny linear combination between the states where you haven't occupied and states you have occupied as a pair. And it's easy to add this annihilation operator on top of it. It is dp of cosine. dp acts on vacuum state, so that vanishes. But when bp acts on this state instead, you lower 1, so it gives 0, 1 state with a coefficient of cosine and sine. When you have this one instead, b dagger acting on this one is 0, because you cannot occupy this state anymore. On the other hand, I can raise this minus b to 1. That comes as sine and cosine. So this one acting on that state, this one acting on this state would cancel, and so that it satisfies this condition that is annihilated by annihilation. And this is what is called the BCS state. So the idea of body group and Schwieffer is that you do this for every pair of momentum. You take linear combination of unoccupied by a pair. You look at the state where pair is now occupied. You take linear combination between them for all momentum flows. And that's how you define the ground state annihilated by this new annihilation operator for all momentum. But as you see immediately, that this linear combination is important only when you are near here, where you have both sine and cosine comparable to each other. But when you're down here, sine is 1, cosine negligible, which means that you can occupy the pair. And that's something we know from Fermi gas. I'll get to you in a moment. when you're way up here, cosine is 1, which means that you don't occupy the state at all. Again, that's what we expect from the picture of the Fermi gas. But near the Fermi surface, you have this linear combination which is sizable in both components, and that's why all actions actually here. So if you ask the question, how many particles occupy individual momentum modes? Here they are all occupied. And instead of going to a step function of going to unoccupied, you smoothly go from occupied to unoccupied in the sense of this quantum linear superposition between the two. Somebody's calling. And so, and if you actually go to the real superconductivity, it does become more complicated because this delta may not be independent of momentum, and you have to solve some self-consistent equation and so on and so forth. But this is already a good enough sort of simplified version of it, where you can see that this Bogoliubov transformation can diagonalize the Hamiltonian in the presence of the condensate. And then you find this BCS state as the ground state of the Hamiltonian. And you see this smooth transition from occupied to unoccupied. Instead of step function, you have this continuous change from occupied to unoccupied. So the Fermi surface is now a little bit smeared. And that's what happens in this kind of fermion by the fermion bicondensate. Sorry, I made you wait.
Does one of the creation operators for the excited state have a negative sign?
Which part, I'm sorry?
For one of the creation operators for the 0, 0.
One is creation operator.
Above.
This one?
No, to the right.
So this B diagram of minus B, I mean, right?
To the right.
To the right?
Before the 0, 0 vector. To the right.
C dagger P, C dagger minus P, 0, 0.
What?
Oh, so there's a minus P?
Yeah.
This is minus B, yes.
Oh, okay.
Okay. Yeah, so you wanted to have this clarified. Yeah. So this is creating particle in momentum P, creating particle in minus P, and they always come in pair to make sure that it doesn't change the momentum of the ground state.
Okay.
Thank you for asking. Any other questions here? I'm sorry I went back and forth several times. Okay, I hope at least the picture is clear enough.
I have a question about the Hamiltonian up there. Again, I know that there is like a sum in front of it, but in this case, it's a sum over all the momentum that are positive, right? Like,
Yeah.
why don't we just like merge the two terms into just one sum? Like, why are we bringing both terms together?
Yeah, because in the end, I should sum them over only the pair, so half of the momentum space.
Why don't we like don't do all of it?
Well, I'm actually cheating a little bit. If you have to sum over all of them, I have to sum over, for example, CP, C minus P, and C minus CP.
Yes.
And because of anti-commutation relation, this vanishes.
Okay.
And what's going on here is that I'm cheating a little bit because I should have actually kept
The spins.
the spin indices. Then, if you go to P to minus P in this big sum, you have this, which is not the same as that one, so it doesn't vanish anymore.
Okay.
So to actually work out this BCS state more carefully, this is the simplified version as I said, but for the all sets of momentum modes, I do have to include the spin degrees of freedom to make sure that your Hamiltonian is not identically zero for some reason.
Okay.
And that's exactly the same thing when you ask the question, what happens to the Lagrangian? Because in the Lagrangian, we include this interaction term.
Yeah, and then we must have different spins, otherwise fair
Right,
enough.
exactly. So, as you point out, Alessandro, this time is that is again identically zero. The only way you get non-zero interaction is when you actually include the spin degrees of freedom, like this.
Okay.
So I'm cheating a little bit here, just so that we can simplify the discussion without including spin degrees of freedom. And as long as I'm keeping only P and minus P pair on a standalone basis, everything I'm doing here is still correct. But it doesn't carry over the full Hamiltonian. So that's why this is meant to be a simplified version.
Okay.
So that's an excellent question. So you're pointing out what I'm sort of trying to gloss over.
I'm sorry.
But nothing seems to escape your attention. Any other questions? Yes?
It's sort of weird. Is the BCS state for the
BCS state.
yeah? Is that a definition by the equation about C x on the current state?
Yeah. So you can say this is a definition, or most people take this as a definition. Either way is fine.
Okay, and these are
Equivalent because I just solved this condition
yeah.
explicitly using the original creation relation operator B. So this is the condition that is violated by the new annihilation operator. And this state is defined by the original creation relation operators. But because of that explicit relationship, I have shown, or at least said it verbally, that solution to this condition is indeed this one. And if you take this state, you can check that it satisfies this one. So this condition and that state is in one-to-one correspondence. They mean the same thing.
Okay, but the annihilation operator acts on the ground state.
Yes.
T plus 0. It sounds like the ground state is similar to the vacuum state.
That's right, but it's not vacuum in the sense that it does have electrons in it,
Yeah.
or lithium-6 atom. So you have this system of fermions, and you know what you're talking about as an atom or electron. And your ground state turns out to be not the number state, again, just like for the coherent state of the bosons and condensate. It's the linear superposition between them, where electron doesn't occupy the state, or electron does occupy the state, and you take the linear superposition between them in a quantum mechanical fashion.
Okay.
Am I answering your question?
I think it's sort of the model.
Okay, all right. So if you have more questions, just let me ask. And then, after doing this, you read off the excitation energy. And the piece that looks like C dash of PCP, and coefficient here turns out to be E naught squared plus delta squared. And remember, E naught is P squared 2m minus mu, which has a spectrum I wrote just a minute ago. So this was the original P squared 2m minus mu. If we switch the whole, excitation energy looks like this. That's E naught. But now I have this delta squared in addition to it. So what it does is to do this. So exactly at the Fermi energy, E naught can vanish, but delta is there, so there is a finite gap. That's why delta is called the gap parameter, or simply the gap. Meaning that it costs you finite amount of energy to create excitation now. Before the gap, it went all the way to 0. That's why there is no energy cost to create an excitation for the Fermi degenerate gas. But now it costs you finite amount of energy. In realistic superconductor, this is actually tiny. So I told you already that if you look at the typical piece of metal, Fermi energy is of the order of like 10,000 degrees, like 1 electron volt. But typical energy for the gap may be 10 to the minus 3 electron volt, milli-electron volt. So this is really tiny compared to the overall scale of the problem. And that gap basically tells you how stable your superconductivity is. One way that becomes unstable is that when you go to high enough temperature, you can start exciting this gap a lot. And if you excite this gap excitation a lot, we assume this coherent condensate, the BB has a finite number, but thermal excitation starts to screw that up. So that condensate then eventually would disappear. That's one way that becomes unstable. And another one is when you think about the overall flow. So we talked about Landau's criteria that if you have macroscopic obstruction, you let the current flow. Can you produce a microscopic excitation by conserving energy momentum? That condition turned out to be drawing a straight line, V dot P, where V is the velocity of the macroscopic flow, if you can satisfy energy momentum conservation by looking at the crossing of these two lines, these two curves, then you can create this microscopic extension. Therefore, macroscopic flow would end up dissipating into a large collection of microscopic excitation, then it would eventually stop, and that's the viscosity. But when the velocity is low, thanks to this gap, you may not find a solution to energy momentum conservation, then you cannot create this microscopic excitation, and therefore there is no dissipation, which means that your macroscopic flow will keep flowing without any resistivity or viscosity or electrical resistivity, if you're talking about a charged superfluid, namely supercurrent. So that's why this actually leads to a superfluid. And indeed, people have observed superfluid with liquid helium-3. The liquid helium-3 is a fermion because it has odd number of nucleons, 2 protons and 1 neutron, with 2 electrons outside. So overall, this is a fermion. And this becomes a superfluid at a temperature much lower than liquid helium-4. Liquid helium-4 becomes superfluid around 2.75 Kelvin, but the liquid helium-3 becomes a superfluid at a millikelvin temperature, so it's much lower. We can talk about cold gas of atoms, like lithium-6. And then you are talking about superfluid, or superconductor, when you're talking about the electrons in some metal like niobium and so on. So what we'd like to do next is, now that we talked about this general picture, I'd like to focus on what happens with a superconductor, because that is actually very useful for practical purposes. Okay, so again, I apologize that I went back and forth on several parts of the discussion, but I hope the basic picture is clear, and I fill in the gaps in the lecture notes and slides.
What's the subject of the B and P?
This B.
Yeah.
So this is the energy spectrum of the excitation as a function of P. This is something we just worked out over here.
What I feel really is that if the dissipation really goes on, since the slope, there is a crossover there.
That's right.
And then the slope will slowly decreases.
Right.
And then eventually they will somehow, and all of the situations will reduce to superfluid.
That's right. So if you have the superfluid, which has the velocity faster than a critical velocity, then it would dissipate and start losing its energy. But if you are below this critical velocity, then there's no way to dissipate by conserving energy momentum, so it keeps flowing without any resistivity.
Okay.
And in the case of the superconductor, and I put that reference also in the slides, by creating a superconductor that looks again like a donut shape, we talked about in the case of superfluid, the current keeps flowing, and people observe that supercurrent keeps flowing even more than a year, because there is no dissipation. Okay.
So basically, every general current is destined to be a superfluid.
Yeah.
I'm sorry?
Like, so every material, every gas.
No, that's not the case. So
Is it
it turns
because-
out that there's some
sorry.
competition going on.
Okay.
So the how superconductivity works, in fact, because that's exactly what I was going next to. It's unlike the case of the cold atoms.
Yeah, exactly.
You need to have some attractive force between electrons so that condensate forms. But we all know that electrons would repel among each other because of the Coulomb repulsion of the same charges. The only way you can have this attractive force is that when two electrons are somewhat widely separated on the lattice, let's say you have an electron here, then you will have electron over there. And let me draw both lattice. And of course, on every lattice sites, you have positive ions. So some of the electrons are still bound to nuclei, and typically only the valence electron starts to wander out. So most of the sites are occupied by a positive ion. They have let the electrons get out of them and start to wander around. So every site has a positive charge. And when you place an electron over here, those positive charges get attracted to the electron. So the lattice actually deforms a little bit. So it looks something like this. So these positive charges start to approach the electron that's over there. And if you look at this situation from afar, you see there's an electron, but in addition to it, there's an accumulation of the positive charge. And then here's the complication. Depending on the material, the accumulation becomes so large that overall, the charge in this area might appear positive instead. But for certain other material, the accumulation may not be as large, so this may still look like a negative charge. So depending on the material, if this overall the area looks like it's positively charged because of the accumulation of the ions around the electron, then this electron sees a positive charge over there and gets attracted to it. So it depends on the details of the material at the end of the day, where this happens or not. But nonetheless, you can have the situation that two electrons can attract each other. And when that happens, as we just talked about, what used to be this step function Fermi surface gets destabilized by forming this pairwise condensate, which is called the Cooper pairs. So in some sense, you have a very loose bound state of two electrons. And as a result, an annihilation operator of electron with opposite momentum end up having this condensate. Then application number now becomes this smooth interpolation between 1 and 0. Then you develop this finite gap and superconductivity. An obvious difference from liquid helium-3 is that helium-3 overall is an atom, which is electrically neutral. So even when it flows as superfluid, it doesn't carry any electrical current. But if we have the situation with the electrons instead, the electrons become superfluid, but when electron flows, it carries electrical current, and that's when we talk about superconductor. So electric current keeps flowing without any problems, any resistivity. So after Cooper's paper, where he pointed out that Fermi surface can become destabilized by the formation of these pairs, Bardeen and Schrieffer joined in and came up with this theory of very, in some sense, surprising idea that you can take linear superposition between states with different number of particles in it. And once again, you need QFT for this purpose, because your Hilbert space contains states with different number of particles in it. Otherwise, you can never hope for taking linear combinations among them, because in quantum mechanics, your wave function has a fixed number of arguments, and therefore fixed number of particles. But in QFT, you can take this funny linear combination, and only by taking this funny linear combination, they managed to find the ground state of the Hamiltonian, and that led to this understanding of superconductivity. And if I remember correctly, the Bardeen won Nobel Prize for this BCS theory together with Cooper and Schrieffer, but he also won Nobel Prize for inventing transistor, and he's the only person who won Nobel Prize in Physics twice. And his son is also a physicist and working in a particle physics today. So it's incredible family. And I don't think there's any questions about that. So the last task for us is to try to understand macroscopic behavior of a superconductor because in the case of the multi-state condensate of bosons, we had a tool already, the QFT basically becomes a classical field theory, and that allows us to talk about current in the donut, talked about this macroscopic flow, and we also talked about these vortices. And all of these things will be discussed using classical field theory. So it would be nice to have again a classical field theory that will describe this macroscopic behavior of the superconductor. But we have a little problem here because the field psi is Grassmann-Off. Its value is not the normal number, it's this weird anti-commuting numbers. So talking about psi as a classical field really doesn't make sense. But at the same time, we also know that the condensate we are talking about is this pairwise condensate. So at the end of the day, what you have to do is to introduce a new field maybe I should put twiddle on it, which is sort of like two psi's in it. So if you remember the case of BEC, it was a coherent state so the field itself had an expectation value. But on the other hand, for the BCS state, you have this ground state. Electron field by itself doesn't have an expectation value, because if it did, you find this weird Grassmann number appearing in physics that doesn't make much sense. But instead, this ground state has two electrons, pairwise condensate in it. So what is non-zero is sticking you two electron fields in it. So what you can do instead is that in the case of BEC, expectation value of the field operator behave as if this were a classical field. So what we can do here is instead putting in two electron fields, two of them in the ground state, will have a non-zero expectation value now. And that is what we can regard as a classical field instead. So this is actually a field that describes a couple pair instead of a single electron. Then we can think about writing down the classical field equation for it, now that there is actually an expectation value in this macroscopic state, and we hope to describe phenomena that has to do with the BCS superconductivity using this psi twiddle instead than of original field psi. So then the task is just come up with field equation for psi twiddle. Okay, any questions about this idea? Everything makes sense? Okay, then how do you actually write down the field equation? So if you actually have two symmetries, so that you can implement overall Galilean invariance in the system. That system doesn't depend on the choice of reference frame. And the fact that you have electromagnetism, it turns out that these two requirements fixes the Lagrangian for psi squared. And this is sort of the modern way of thinking about field theory. You first think about what are the symmetries of the system, and once you know the symmetries, the Lagrangian you can write is already limited, because you cannot put in arbitrary terms. Some of them may violate the symmetry you need. Then it turns out the Lagrangian you write down is already limited because of symmetry requirements. Then you look at behavior at low energy and low momenta, and that actually tells you what is called an effective field theory is. Or EFT for short. And because we're making a jump from the electron field to this field of Cooper pairs, which is sort of bound states of two electrons, you don't necessarily know how to derive the field theory from psi twiddle out of the original field theory from psi. But at least we know you can have the independence of reference frame, and you know there's electromagnetism. It turns out that knowing these two is already sufficient to fix the Lagrangian at low energies and low momentum. And one thing about the Galilean invariance is that basically the kind of Lagrangian we have already seen is the only thing you can write down. And I don't go through this argument here, but again, I put that into slides, and lecture note already has this discussion in it. So it turns out that whenever you demand that Lagrangian is invariant under Galilean symmetry, it has to come with this combination, which is called covariant derivative. And everything has to be in a combination psi and psi dagger with equal numbers, so that its phase transformation I talked about before always cancel. And that is because the Galilean transformation x and t is I mx mvx over h bar minus half mt squared over h bar psi x plus bt t. I think I wrote this on board some time ago. And because Galilean transformation involves the change in phase, the only way your Lagrangian can be invariant for the Galilean transformation is that this phase factor always cancels. Which means you always need to have equal number of psi and psi dagger in every term of the Lagrangian. Therefore, potential has to be a function of psi dagger of psi, not psi and psi dagger individually. Which then means that your Lagrangian, which is Galilean invariant, turns out to be also invariant under psi going to minus I theta psi, psi dagger going to plus I theta psi dagger. And once you have a symmetry, then you have a conserved quantity. That number operator is conserved. And that's Noether's theorem. So that's how we can constrain the formula. But what I haven't actually put in yet is this requirement of electromagnetism. So that's something we'd like to discuss in the next few minutes. Yes?
In which class do they actually teach about Noether's theorem properly? Like, in which class would they derive something like Noether's theorem?
I have lecture notes in the on the B courses, but what What about telling the TAs to talk about this Galilean invariance
Sure.
in the discussion section?
Because it seems to be central to today's physics, and no one seems to be talking of like deriving.
I agree that, and yeah, so let's see. Yeah, so why don't we talk to TAs about that?
Okay.
Okay?
Question?
Yes, go ahead.
I need to erase that.
Oh, I erased it?
Okay, it's fine. Can we understand the ground state of the BCS?
So, you know this equation?
Yeah, the Cooper pair operator, right? Can we understand the ground state is the eigenstate of that operator?
Uh-huh. No, it's not eigenstate. It's an expectation value.
Let's see, but
In the same way that in the BCS, BEC, we have expectation value
yeah.
of the operator.
But can we? Okay. So we cannot just combine the two sides together as the operator and acting on the ground state. So it's okay.
Is that okay?
Oh, I sort of know it.
So if you take, remember again what's going on with the coherent state of the classical quantum harmonic oscillator. An annihilation operator in the harmonic oscillator has an expectation value. And when the expectation value is large enough, then you can pretend that that's sort of behaves similarly as a classical pendulum, because you
Yeah,
fix it
I
here.
want to ask, what's the classical counterparts of that classical field?
This one?
Yeah.
Yeah, the classical counterpart is what describes this macroscopic flow of the supercurrent. And that's what I'm trying to tell you now.
Oh, okay.
Okay? So let's get to that. But there's additional requirement that we have this electromagnetism. The electromagnetism actually requires something called gauge invariance. And this is something you know from classical electromagnetism. What you need is electric and magnetic field describe electromagnetism. But instead of using electric magnetic field, it's easier to talk about vector potential and scalar potential when you solve Maxwell's equations. But when you do so, there is actually an ambiguity of changing A together with some arbitrary function chi, and here is the gradient of that. And scalar potential is changed by the time derivative of it. And when you plug in this change in here, this change in vector potential is curl of grad that identically vanishes because different components of the derivative have to commute. If you also do the change looking at the electric field, this A dot changes by time derivative of this gradient chi. Phi changes by the grad of time derivative. And thanks to this minus sign, they cancel. So the electric and magnetic fields don't change. So when you introduce vector potential and scalar potential, there is an ambiguity in this vector potential and scalar potential. Then what you have to make sure is that when you actually do these changes of vector potential and scalar potential, physics doesn't change. If it does, then you're screwing up your electromagnetism, because at this stage, vector potential and scalar potential was meant to be just a tool to make it easy to solve the Maxwell equation, not something meant to be physical directly. So you have to make sure this ambiguity does not change physics. So some people call this a redundancy of description. So let's think about how one works. And if you remember how you introduced electric and magnetic field in quantum mechanics, And you have a wave function of the electron. Then you have with Schrödinger equation like this. So charge times scalar potential is the potential. So if you have an atom, the nucleus produces the Coulomb potential. That is in phi times the charge per electron gives you the potential for the electron. So that's the piece we need. When you have the magnetic field, this is a combination usually called P minus EA. Okay, times I guess. And you write P minus EA squared to describe the electron in the magnetic field. It turns out that this is actually very important because this is the only way you can maintain this invariance under this redundancy. So it turns out that when you actually change A to A, in here I need to be careful with the sign, and phi to phi minus chi dot. It looks like you have a new Schrödinger equation. Then it looks like we have changed physics. But it turns out that when you also change psi at the same time, to psi, which is function of both x and t, to psi prime, which is related by this phase e to the IE chi over h bar, where this chi is taken to be the same chi that appears in the change in vector scalar potential. And here's the charge of the electron here over h bar. So at the same time of changing A to this one, phi to that one, but also changing psi to psi prime together with this phase factor, it turns out that you have really not changed anything. So it turns out that when you actually take time derivative of psi prime, in addition to IH bar ddt acting on psi itself, you can also take time derivative of this exponent that gives the additional term like this dot times IH bar, H bar cancels, I becomes minus. So on the left-hand side of the equation, I get two terms now where the time derivative is acting directly on the original wave function, and then I have this additional term of E chi psi. But if you look at this piece, E chi dot psi, I'm sorry, this piece is precisely the change on the right-hand side, so that they cancel. And if you keep going, the spatial derivative inside this P can also act on chi. So this spatial derivative would extract the derivative of the exponent. This is E gradient chi. 1 over h bar cancels. It is a factor of I. And this additional piece would cancel changing A by grad pi, because it's multiplied by E grad pi. That's exactly the combination I get by hitting this spatial derivative, hitting this exponent pi. So it turns out that if you just work this out carefully, together with signs and everything, doing the change at the same time of changing vector potential by this amount, changing scalar potential by this amount, and also changing the wave function by this phase factor, does not change the Schrödinger equation, where this phase factor just factors out from both sides of the equation. And that's how you can guarantee that this redundancy in vector potential and scalar potential does not affect physics. And this change in A and phi and psi at the same time is what is called the gauge transformation. And gauge transformation is a funny thing here, that you are changing phase of the wave function arbitrarily for one space-time point to another space-time point, because chi is a function of x and t. So one sort of fancy way of saying it is that the phase of the wave function never matters, and when the phase only matters when you are looking at the relative phase of two wave functions at the same space-time position. So if you're changing overall phase at the same space-time position, then that should not affect physics. Therefore, it should be okay to change the phase of the wave function arbitrarily from one place to another. So that's the idea of changing this invariance under the change of the phase, which was meant to be a constant phase in all space and time, but to a local change in phase. And when you change things locally, the Hermann Weyl thought, that's sort of similar to changing the unit of space-time dimensions arbitrarily from one place to another, and that's how we invented the name gauge transformation. But he was wrong. We are not changing the unit in any way. We are only changing the phase of the wave function. And but name gauge transformation got stuck. But once you know that your Lagrangian Hamiltonian has to be invariant with gauge transformation, then you know how to write down the Schrödinger equation, or in our case, Lagrangian. So it turns out that all you have to do is that whenever you have time derivative, you change the time derivative to the combination of time derivative and the scalar potential. Whenever you have the spatial derivative, you change this to the combination of derivative and this vector potential. And you also change the field psi by this space-time dependent phase phi. And this combination is the gauge transformation. Gauge invariance. So all you have to do is to go from the Schrödinger field theory we already know, is to replace this psi dot by this, replace this spatial derivative by this, and when you change phi and a according to that change in redundancy, together with this phase change in the field psi, then this Lagrangian is invariant. But you can't write time derivative separately from the scalar potential. You are not allowed to write spatial derivative separate from vector potential. If you do, then you screw up this invariance that this gauge transformation does not change physics. So based on this requirement that physics should not depend on changing the gauge of vector potential and scalar potential, your Lagrangian is more or less uniquely fixed. Then comes a very interesting fact. Now that there is a vector potential inside this field, and I finish in 2 minutes, and this corresponds to the Cooper pair. So psi leg of psi should correspond to the number density of Cooper pairs, which is the half of the number density of electrons, because each pair has 2 electrons in it. And another thing I have to mention is that this m is supposed to be mass of the Cooper pair. So twice the mass of the electron. But otherwise, we have this usual interpretation that psi, now for the group pair, is constant density. And then we take the square root. In the case of boson, that was what used to be mu over lambda. And using this, if you plot the E here, you find the term out of this where I insert vector potential inside and for constant expectation value, derivatives go, but this vector potential piece doesn't go. So this ends up giving you E squared of H bar squared, A squared times the number density. This is the term we didn't have before. Normally we think psi doesn't have an expectation value, but now there is. And then if you write down the Maxwell equation in the presence of this term, so you add together with for the Maxwell field, together with this you take the variation. Then from this one you find rho v, and from here you find so your equation has a new term in Maxwell's equation. And if you solve this equation, you find that magnetic field on the edge of the superconductor with this magnetic field going this way with big size, because of this term, it starts to dampen exponentially. So just by solving this equation, you'll find the magnetic field does not penetrate into superconductor over a certain distance for the mode of penetration. In order to see what is this new term here, you can work out what this depth is in terms of these fundamental constants, together with the density of electron in the system. And that actually gives you a certain number, how much magnetic field can penetrate into a superconductor. So the magnetic field, which we know is a long-range field because your compass would point all the way to North Pole over planets, has become a short-range force inside a superconductivity. And also in the same way that once you have the field equation, you can look for vortices, and you can find solution for the vortices where you really see the supercurrent sort of going around. I hope you can see it. And you can indeed find those vortices punching through a piece of superconductor. Again, you see this beautiful triangular lattice of the vortices, just like what I've seen for superfluid. So this is again a macroscopic coherent behavior of a quantum system, just like vortices we have seen in superfluid. And those vortices can in principle move. In the slide, if you look at it, there's a link to animation where all these vortices actually move around. As a result, when you apply magnetic field, it gets repelled, but it can actually squeeze into vortices and penetrate through a superconductor. And this magnetic field is called abricosol flux, which penetrates through the magnetic field. And if you do superconductivity in laboratory, you see this piece of superconductor floating on a permanent magnet. And the reason for that is that the superconductor gets pinned by this magnetic field going through it, so it's not easy to move it around anymore. If you try to flip it around, magnetic fields have to first get repelled and re-enter the superconductor, and that requires a lot of work. That's why it stays floating on a piece of magnet. And that's how you can build a maglev, the kind of train that floats. And that's because of the superconductor that doesn't have electrical resistivity, it can keep flowing, but also can float on a piece of magnet. That's why it can run at an incredible speed, like 600 kilometers per hour, without much of shaking going on. So you don't get totally dizzy on a train ride. It can go very smoothly because it's floating and it doesn't touch the rail. So all of these things can be described by, again, the field theory Lagrangian. Once you accept that your field is a field that describes the Cooper pairs instead of individual electrons. So I realize I rushed through the last part of the discussion, so let me repeat some of that on Wednesday, but I definitely update my slides to incorporate these discussions. And just by working out is what manual penetration depth is the first problem set in the midterm exam. I have given you the equation, so you don't need to work it out, just plugging in the numbers and to see how short this distance is in a piece of superconductor. So that's the beginning of the midterm. So good luck with it. Sorry I went over time, and I'll fix the slide and I announce that one thing. Thank you.